And we are live. All right. Hello, everyone. Hello, Geeks. So today we are going to take everything we did last time in the latest streams, I'd say, and we are going to pack them all together and see how people in real life, in science, are using these tools to develop their own platforms, to develop their own way to manage workflows, and to also being able to exploit resources that are outside their range, usually outside the range using normal cloud computing paradigm. So without further ado, I introduce our guest today that will guide us through this real life use case. And so please welcome Matteo that accepted to be with us today. So thank you, Matteo.
Hi Diego, thanks for having me. It's a great pleasure to be here. I've been watching a couple of lives of yours. They're always very nice. So it's very nice to be on the other side of the screen, let's say, for once.
Yeah,
So,
cool. So yeah, my idea was actually to introduce a bit what we are going to see today and how this relates to what we did last time. So just let me show briefly retake our old friend here. So yeah, last time we left with this awesome guy here that wanted to use a Kubernetes cluster to submit its payload. So in our use case before was Jupyter Hub for interactive development. In this case will be slightly different what we see today. So suppose that you already develop your machine learning model or the way you want to train your machine learning model, you can containerize it. And then once you containerize it, you want to submit a pod actually to a Kubernetes cluster. And once you do that, the idea is, okay, I don't care anymore where this container will end. And the example that we are going to see today is that this red box in here won't be necessarily a physical node of a Kubernetes cluster, but will be a virtual node, one of them that we saw last time when we show interlink. So the way to create a virtual node on an HPC center. And in this case, so just let me update this. This will not be a physical node, will be a virtual node on, okay, let's scroll down a bit, on VEGA HPC center. So, and the cool thing is that in this setup, you run all your machinery inside this container that is running, you don't know where. And then you can talk and collect all the metrics that you need thanks to the latest tool that we showcase, that is the MLFlow instance with a persistent storage on object storage. So I'm sure that Matteo will tell more about this or this circle, but just let me mention that I'm going to have for each one of these components a video recap very soon to summarize for you to make you able to reproduce step by step everything we are doing today. All right, I have done everything for today for the introduction, sorry, and so I will left the stage to Matteo, but first, before starting, just 1 minute to see if in chat, okay, where is the chat? There is anyone that want to say hi or already a comment or a question. Okay, TikTok.
people are busy.
Yeah, we are all waiting for your demo, so
Okay,
I suppose we can go ahead. Right,
okay,
cool.
okay.
So, please, Matteo, tell us more about your use case. Introduce yourself, or do whatever
Yeah,
you want. Just
sure. So, well, I'm working at CERN, and I'm working on a European project which is called interTwin. And of course, I'm not alone from CERN. There are also other very nice colleagues I'm working with. So, and we are splitting, let's say, between working on a use case that CERN is providing to the project, which we will see in a few minutes, and let's say the development of the core AI tools to support, let's say, large scale machine learning workflows and workloads on cloud and HPC. So basically, to unpack this a little bit before starting, actually my main focus is on, let's say, helping the researchers to scale their machine learning workflows to HPC resources when it comes to training, to leveraging the federated European infrastructures, which sound like very big buzzwords, but in practice it means that in Europe we have many HPC centers. And researchers can apply for compute time on them for free. And so our goal is to, I'd say, help them to scale their machine learning workflows to HPC resources, which means hundreds or thousands of GPUs. Because nowadays we know that AI. I mean, you cannot do AI without tons of resources. It looks like the current trend is foundation models, or let's say transformer-based models, language models. So also in science, this is let's say becoming more and more popular. Our goal
Yeah,
is
so, yeah. Just a comment at this. So this is why it's also interesting to look out the window and see what other players are doing, because our use cases slowly converging toward a common denominator. So yeah.
yeah. Exactly. So let's say that historically, scientists were used to train their even machine learning model on just laptops or simple on-prem nodes. So I have my node, my VM with one GPU, with four GPUs, and it's enough. But nowadays we have larger and larger data sets because, I mean, ML is becoming more and more complex. So we need richer data, and but we also need more resources to process all of this data in a, how to say, feasible time, because you can still train how to say, like GPT-4 on 4 GPUs probably, but I mean, it will take probably years. I don't know. So the thing is, how can we accelerate science? So how can we, I'd say, lower the entry barrier for scientists, allowing them to leverage all these resources that are already there, actually. So, but ML, as you said, is becoming more and more complicated and more complex. So it's not about resources anymore, but it's also about services. So um, again, imagine you train your model on your laptop. I mean, you save checkpoints on a folder, but then how do you share these checkpoints or models with your colleagues? Or how do you compare the models that you save there with the models that your colleague, I mean, just sitting beside you? I mean, how to compare these models? I mean, again, there is a lot of, let's say, tedious work that you should, you will need to do. A lot of like also, let's say, engineering work, because if you want to set up some custom services, you need to do them on your own. But hey, on the other hand, there is cloud. So why not leveraging cloud, and why not leveraging all of these very nice technologies that, I mean, as you were saying, are becoming more and more popular and more consolidated, like containers, Kubernetes, but also, I mean, containers and Kubernetes are very low level. I would say even higher level services.
Yeah, I think that you touched the main point. So I tend to consider Kubernetes a good starting point if people don't see it. So really,
Exactly.
what really counts is what you put on top from the user perspective. So yeah, how is your use case and why we are talking about MLflow in this case? So
Hmm.
yeah.
Yeah. So again, like talking about resources. So CERN in general, a physicist, they need to, when they collect data from the LHC, so from the Large Hadron Collider, from the big accelerator, and from the experiments attached to that. But then they want to verify that this data is, I mean, they want to compare the data that they collect with some well-known physical models that they know. And so for this reason, they need to simulate roughly as many data as they collect. And so the more data that they collect, the more data they need to simulate. And simulating data nowadays is extremely compute intensive because it's done through Monte Carlo methods, which are a set of algorithms which work in a step-by-step manner. So they are hard to parallelize in the sense that, to predict the location of the particle at the next step, you need to know where the particle was at the previous step. So it's not extremely easy to parallelize them. Okay, so let's say that historically, we have, CERN and in general, the high energy physics community has relied a lot on, let's say, simulation and let's say numerical methods for simulation. But the question is, why? Isn't there a way to speed up these simulations? So here, fly. So as you can see here in this picture, we have an example of interactions of particles inside a medium. So you see, like they will interact with the material and be scattered around, and all of this scattering is simulated mathematically. But the question is, and here we have a GIF, if I remember. Let's see. Okay, it's not a GIF. So in the detector, we have these things which are called calorimeters. So the calorimeters are activated when a particle strikes into them. Okay, and as you can see, we have like an exponential number of particles that are generated, and this means that when we want to simulate this exactly numerically, it takes a large amount of resources. But the question is, isn't there a way to make this quicker? Well, actually, people at CERN and other people that are working with me, for instance, Calliope Solaki, they are actually working, and Sofia Valcorsa, for instance, they are working on investigating, they are investigating on new methods that use AI to speed up these let's say, numerical simulations. Okay, so we want to solve this at least reduce this bottleneck when it comes to generating particles data. Of course, this data then, it cannot be used in all the applications, but there are some domains of application in which AI generated data is still valid and is still, let's say, a good, let's say, candidate. Okay, so going back to the problem. So now we have a use case to solve. By the way, maybe Diego, then you can share the link to this website. There are a lot of resources.
Yeah. I'm doing.
Yeah, if people want to know more.
Yeah. I put in the chat and
It's
overlay.
public.
So
yeah. Anyway, the goal is to train a generative model, and at the moment we've been investigating GAN, so generative adversarial networks. But any kind of AI-based generative model is good. And as the image is showing here, so we generate some data using like numerical methods that will then be used to train the machine learning model. So anyways, let's take a step back. Now we have defined the problem that we want to solve. Now let's see how we can solve this, and let's see how we can use HPC resources, and how we can see. Yeah, sure. Let me enlarge a little bit the text. So let me see. Let me know if you can read it. So anyways, so now the goal is once we have defined a problem that we want to solve, which is like critical problem for the high energy physics community. So how do we speed up the generation of data? So let's see how we are going to solve this problem using HPC resources, which are made available by the by the EU, European Commission. So let's say HPC and the cloud. So the goal is to put together these two different words. HPC, so high performance computing, where we have the heavy lifting, the number crunching, and on the other hand, the cloud, where let's say usually we don't have GPUs, we don't have hardware acceleration, but on the other hand, we have lots of interesting services like MLFlow that I think you already introduced. So on cloud, we can deploy a lot of services that then will be used by the users. So the goal in the end is to put together these two different worlds. On the one hand, we have HPC with extremely powerful resources but sort of isolated on its own dimension. Okay. And on the other hand, we have cloud, which is extremely interoperable. We can deploy services. We can have different users log in. We have like web front ends, extremely user friendly. So how can we put these two things together?
Yeah,
So I think,
in a
yeah,
certain sense, yes, exactly. This is nice to see, because essentially what you're doing here is what we commonly called in interTwin project, for instance, this is an offloading, right? So you
mhm,
have something heavy that you want to delegate somewhere else. And the point is, okay, good, I have actually something that can run heavy things. Let's see how we can do that. So yeah, please go
yeah,
ahead.
exactly. Yeah, indeed. Also because even at CERN, although CERN is pretty large, as big computing facilities, but still, let's say historically, the computations in the high energy physics were running on CPU, which is different from AI. AI it mostly needs GPUs. So you see, there is a sort of a new paradigm which is coming, and of course the procurement takes time, takes years to update your on-prem resources. So of course one option could be, okay, let's buy the resources on public cloud, of course, but then you need to pay for that. So since we already have these free GPUs on European resources, why not using them again for free, right? So um, in the end, what we want to achieve in the interTwin project is this. So the user will have like a simple, let's say, front end, which interacts with the cloud. So the cloud, in the end, you can imagine it as the user front end. And on the cloud, we define some workflows. So in this case, AI workflows, like generate some data or load some data and do some sort of preprocessing and any kind of machine learning workflow. And then after that, we submit the execution of the workflow. But as I said, during training, we need lots of GPUs. We may need lots of GPUs if we want to use large models like transformers and so forth. So then what we want to make it possible for the researcher is to flag one specific step in the workflow to say, okay, this is a GPU hungry, let's say GPU intensive workload. So please offload this to HPC and execute it on HPC. Which sounds pretty neat, pretty straightforward too. But then the thing is, when we work with machine learning, we are not just running, training, and that's it. And yeah, so but we also generate some data with let's say the execution of a machine learning job, right? So imagine machine learning logs, like the accuracy that the model is achieving at each step of training, or the model checkpoints, the best model, and so on and so forth. So as you can see, then here from this drawing, there is something missing. So we launch the workflow. The workflow manager is executing the steps. One step is running on HPC, but then this step is generating some data. But the data now lives on HPC. So this means that the data, like the ML logs, the model checkpoints, and similar, are not available on cloud, and they're not available directly to the user. So how can the user, let's say, access this data? Okay, so an idea could be to utilize an MLflow tracking server. So we deploy on cloud, and let me zoom a little bit more. We deploy on cloud an MLflow tracking server, which can be reached from outside. So assuming that on the compute nodes of the HPC system, we have internet connection, then we can close the loop, because we offload the machine learning training to HPC, and the job running there inside an obtainer container and managed by Slurm will be able to log back on the MLflow server, which is running on cloud. Okay.
Yeah, just sorry to come in, but
Yeah, sure.
the connectivity is a good point. I also think that if this becomes a large enough use case, you can also think that at the HPC level you can have some kind of edge service exposing MLflow server, right? So you can
Yeah.
both access the MLflow server from outside and from inside the perimeter, let's say, of the HPC. So that can be a possibility. So it's not really, what I mean is not really matter of I don't know, the network topology. It is more like the idea of delegating somewhere else, being able to report back the results. So I see this really like a runner module, mode of operation. Some when you have a GitLab or a GitHub runner that is running somewhere else, you send their work to be done, and it reports back the results. So yeah,
Yeah,
that,
pretty
that
much.
is pretty nice for that reason.
Let's say the only difference is that I imagine that the GitHub runner can sort of be uh, decentralized, but in this case we need a centralized entity, which is the database. Like in this case, the S3 storage, for instance, that keeps the ML logs in the same place for all the researchers interested in working together. Because, like, imagine that one time I'm offloading to some HPC, but then I'm offloading to another HPC if I'm working on multiple HPC, or anyways, like I need to keep let's say, the database consistent. So, okay, yeah, sure. Indeed, it doesn't matter.
You need a data lake, right? So, sort of.
Yeah,
So
yeah,
that's
exactly. So
probably
also,
another stream. So
exactly. And also, yeah, well, I don't know, maybe we can cover this later, or I can just, go quickly through that. But again, like the ML training needs some data, right? So on what data do we train? Well, yeah, we need a data lake. So as you said, like in interTwin, we're using a Rusho-based data lake. So the idea is that then the data sets can be shared between cloud and HPC using this distributed, let's say, dataset, this abstraction that keeps the datasets consistent across different computing sites. Okay, but again, like as you said, uh, like maybe we could even use the data lake to store the machine learning logs. So at the moment, this is not possible out of the box because MLflow doesn't. I mean, the MLflow, let's say, protocol, let's call it this way. So the way MLflow stores data is not directly compatible with Rusho. Um, we know that there is a possibility to implement some MLflow plugins to extend the, let's say, MLflow and make it available. I mean, allowing it to use different storage technologies, such as let's say Rusho compatible technologies. We will see if this is possible. But yeah, exactly. So in this case, the MLflow logs could be stored in the data lake, and then we sort of have the guarantee that they are kept consistent across all the computing sites. Okay. So, but maybe we can talk about this a bit later in more details.
yeah,
But
just
now
not
let's,
to scare people. So we are
yeah,
not looking at this red line today, right? Probably in the
exactly.
future we will,
No,
but
no, no, exactly,
right now we are looking at the orange stuff.
exactly. So let's go
Okay.
back to the orange. Let's go back to
Okay.
safety. So yeah, today we're looking at this in particular, exactly. So today we're gonna run the orange. We're gonna walk on the orange path. Okay, so we don't care about the data lake. It's just to let you know a bit more the background of the infrastructure. So let's move to the, let's say, to the demo. Oh, let's close this Docker file. So very good. Um, so maybe, I mean, should I do like a walkthrough of the code, like what we're training, or maybe we
Yeah,
just
yeah, I think we can start just a second to take questions
sure, sure,
if
let's
are
do that.
any.
I'm
And
here.
yeah, so while I'm loading, so let's take some questions if there are any. And I put the overlay of the chat in here. Okay, and while I'm doing this, I'm also taking my terminal back to show you one thing. So a preparatory step, if you want. We say that we are going to offload stuff to an HPC, and I just want to be sure that you agree we are not cheating. So I'm logging into Vega Edge service where we install all the interlink part. So where we have the Slurm client working and all the, if you do ps grep interlink ps folks interlinks. Okay, trust me, these are all the processes that are running the interlink component. And we have here the queue from the Vega system. SSQ minus me. And you see that there are no jobs now running. So when Matteo is going to run its pod, we are going to see that the jobs are going to appear here, and yeah, so the magic actually happened. And yeah, hi Daganorov, hope to you're well. If you have a question, please drop it in the chat. All right, so yeah.
Yeah. Anyways,
Now
there
that
will be
we are
time.
sure that there is no trick behind the scenes, I can give the stage back to you, Matteo. Yes, please guide us briefly.
Sure.
Probably if you still can increase a bit the characters, we can read it better. Okay, good.
Okay.
So a quick tour to your workflow and how actually the magic happens for both the MLFlow reporting and the offloading to a Kubernetes node, virtual node.
Yeah, and then let's say that if there will be question, there will be time, because I mean when we execute stuff, it will take time. So I
Yeah.
mean, there's okay. So as I was saying, we're training generative models, right? So we're training a GAN. We have a generator. Okay, so we're working with torch-based models, but actually we're working with PyTorch Lightning in this case. But it doesn't matter. We can use whatever torch. Or TensorFlow. I mean, actually, interlink doesn't even matter what ML. We could even use JAX or what. So again, like we have a generator discriminator. Then okay, in Lightning we define our Lightning module, right? So yeah, okay, you can look at all of this code on our repository. It's called Between AI. Maybe I can show it later. But in general, we have some training. So yeah, is a GAN, right? So generate some noise, which we pass it through the generator. We compute generator discriminator loss. We optimize, and that's it, right? So then we have some. Let's see if I can show you some additional things, but yeah, pretty much. So we're running. So we have a training step, a validation step. This is important to consider. So in the validation step, we will consider the generator loss because we're training a GAN, and yeah, and then we also have a predict step, but we won't cover the inference today. If let's say the public is interested, next time let's make this a promise, okay? So if we get 10,000 likes, no,
You're
so
auto-inviting yourself. It's cool.
yeah, no, of course. So I'm saying,
No, right.
if we get, let's say, 10,000 10,000 subs, like on Twitch, we get like €2 per sub. So yeah, if we get, let's say, rich out of this live, so there will be a follow up, and we can show not only how to train a model, but then how to pull back the trained model and use it for inference. But we will skip this for today. So we have a model, as I said, and we also have a data loader. So let's say, okay, data loader, let's say all the data management part, again, is storage, is stored Lightning. So we have a Lightning data module. We create our data sets and we split them, given some proportion. And again, that's pretty much it. And since I'm also working in interTwin, I'm also developing my own tool, and the tool is called iTwin AI. And in our case, we are relying heavily on configuration files because we want the machine learning workflows to be reproducible, but also user-friendly. So in other words, we don't want to have like hard-coded numbers into Python scripts, which are very popular apparently. We don't want to have them. and actually we want the researchers to use thanks for sharing the link. So we want the researchers to use configuration files, and which can be versioned. If anyone knows a little bit of infrastructure as a code, I mean, you can understand how nice is to have configuration files. So here we have all the configuration that we can imagine, and since the workflow is sequential, we can even configure it in a sequential way. So we have two steps in this case: the data loading step, which will download the dataset if the dataset is not there, but we won't need to download anything today because the data is already there. And then the training step, right? So in the training step, we have then some PyTorch Lightning configuration, in which we can define some callbacks, like some early stopping, learning rate monitor. So we will see the learning rate later in the logs, some checkpointing, and then we define the loggers, right? So we have the CSV logger, for instance, but what we really care about today is the MLflow logger. So the MLflow logger, the only thing that you need to take away from this is the MLflow logger tracking URI. And the tracking URI, thanks to OmegaConf, is something that we reference from the top. So the tracking URI is this URL, which is the endpoint, let's say the door on which to knock to save our ML logs. And this MLflow tracking server, let me just show you
All right. So
here,
yeah,
is this
it is
guy.
the remote endpoint where we store the
Exactly.
artifacts, if you
Yeah.
want.
Yeah.
All
So
right.
this, which will store then stuff in, let's say, artifacts and artifacts in this S3 storage. So this is the link of this guy. All the code that we just saw will then be executed on the HPC inside a container, which you can imagine like this yellow box here. So let's go on. Well, I think you saw pretty much everything that you needed to know about, let's say, the machine learning. Then if you have questions, maybe it's easier, then I can reply to questions later. So
Yeah,
let's
I see one question, but
okay,
I pinned that so we can answer
perfect.
to
Yeah, yeah.
that afterwards.
Because in a while I'm gonna launch the training, so there will be
Okay.
like 2-3 minutes at least. Okay. So
Then there
now
is just 1 second. There is one other question that is, do you manage TensorBoard logs somehow? If you're
no, in this
using
case we're
Tensor.
not using TensorBoard. We're using MLflow, which is sort of an equivalent. So you can imagine TensorBoard and MLflow like they could be replaced. I mean, like they're sort of
Okay.
interchangeable.
So yeah, I think this is an interested question because we are looking into this, and it's also related to running distributed training. That is a
Mhm.
challenge on its own. And yeah, probably we can postpone this topic at the end where we have the questions and answers, so we can get a summary and a plan for this.
Mhm.
So thank you, Dagonarov.
So let's say that if yeah, I mean in general today we're talking about MLflow, but because it's the easy way to get there, right? But in other words, I mean, we can also use other solutions. If you want. So, anyways, now let's do the offloading. So let me go back to the picture once more. Now we're doing the point one. Okay, so we're defining the Kubernetes pod that will be sent to the HPC to the interlink sidecar, which will then be, let's say, converted. Forgive me for this word, converted into a container. Okay, so we create this pod, we give it a name, and we use some annotations. I don't know if you already explained this in the past, probably yes. So how the annotations work.
Yeah, we saw something not in practice. So if you want to show what
Let's
you're
mention.
doing now, it's good.
Okay, so in this case, so we're submitting this pod to a virtual kubelet, and we are giving some annotations that will be, let's say, parsed by the interlink sidecar here. Okay, so this guy will receive this pod, this, let's say, JSON file or YAML file, and then it will go into the annotation and read them in some sort of order. So now this is the pre-exec is commented, so it will not be sent. But if it wasn't, first thing, it will pull the container image that we want to execute. Second, it will, let's say, for instance, bind this location on the HPC on some location in the container. And to execute the container now inside Slurm, it will pass these arguments, command line arguments to Slurm. So in this case, we're requesting for 4 GPUs. We're asking Slurm to execute the command only once. I mean, to run the container only once. Let's say once the resources have been allocated, we only need 1 node. And we assume that our job will run for up to 55 minutes. Okay, it's just
Yeah,
a number.
the cool thing here is that, as you've shown, you can customize pretty much everything. So the way your pod is translated into a Slurm job can be customized via annotation. That is a pretty powerful way to do things. Just one thing, there is also a part regarding the requirements for the Slurm jobs. So in terms of CPUs and memory, and this will be parsed directly from the container request. So we go down here, you see that we are requesting limits for 48 CPUs and 150 gigs of memory. So this will be the request that will be made to Slurm in the Slurm job to that will be submitted.
Yeah. So let's say that for this simple training, so now I'm just going to run like a light version. Okay, so we just need 20 gigabytes. Probably is way too much. That what we need for CPUs is just for a demo, right? So we don't want to wait for an hour. So it's okay. So and then once we, let's say, specify the resources that we need for the job, could be more, right? I mean, I could just give more nodes here, right? It doesn't matter. I could give 32 nodes. I think it's okay. And then we're going to execute the command. Finally, we're running this command inside the container, which is okay. So I'm going to run distributed machine learning training of the code that I just showed before. So to run that, I'm going to use TorchRun, which is the launcher for distributed ML for data, well, for, let's say, Torch distributed ML workloads. So I'm going to run TorchRun. Again, just 1 node. We're using only 1 node, and we're going to use a number of workers equal to the number of GPUs. So it's sort of adaptive. So in this case, we requested 4 GPUs. So this means that we will have 4 workers working in parallel and processing the data in parallel, which means that we're going roughly 4 times faster. Let's say ideally 4 times faster in training our model. Then we pass some, let's say, we override some fields in the configuration file. So again, this is a feature of iTwin AI. So again, we can change the dataset location. So the dataset location before was like a local folder called expert data, but now we change it with an environment variable, which now is this expert data is mounted at the root of the container. On the root of the container, we can change the number of data set. I mean, the maximum size of the data set. Again, I'm keeping it small now, just 10,000 data points, because I don't want to bother you too much, with waiting for the result. We're passing the MLFlow tracking URI. Actually, we don't need to override this, but just in case. And here I'm just hiding them. I just put some X's, but actually we're also passing the MLFlow credentials. So the MLFlow tracking server credentials. So of course we need also a username and password to log in to this MLFlow tracking server. So they are passed there. So this is like a dummy pod. Okay, I'm not going to run specifically this one, but it's the same.
Yeah, just to be clear, at this point, either you run this pod on a virtual node or on a real one, it should be able to run in the same way, right? Module, if we, with the exception of the image name, that probably will need to be changed, because now we are importing the image directly from the file system on the HPC. But
yeah, exactly. So let's say that,
and that's the concept that we say before, right? You have something underneath, something under the hood that you don't care what it is, and then you have your physics use case that you are packaging in some way, thanks also to iTwin AI, and so you can distribute them without even knowing. Well, quote unquote, knowing just the correct annotation that you need to submit to the
Exactly.
flow.
So let's do a simulation of what would happen. Like let's say I
Yeah.
change something in the code. Like I change this default value. I put 0.8. Okay, this is like an extreme, right? Just change a value. But I mean, by the way, this I could have just changed it from the configuration. But again, like it's an extreme. So I change this. Then I can now I can reveal the container, right? So I will just what is it? Let me just get it. I had it before. So yeah, so here what I'm doing here, I'm building and pushing a new Docker image. So let's change its name. Let's say 0.2, just for the record. So I run this, then a container will be created, and this container contains all the dependencies of my machine learning job, all the code that we were saying, like the data management part, the gun training scripts that I was showing before, like the generator, discriminator, all of it is packaged inside this container. And let me just hide this. So now this container has been pushed to my container registry. So this means that now this container image only lives inside my container image, inside my container registry, which is on GitHub. So I need to pull it, right? So now I will
All
go
right.
into the
Yeah.
I will
Yeah.
go into the
The
prod.
point is that you have a machinery for which you can download your image
Yeah,
into the HPC.
exactly.
We
So
might have something automatic in the future, but yeah, that's the current,
yeah,
let's say, workaround that is working pretty well, I think. So it's not
yeah. I
really.
mean, there is this thing that you need to be aware of. Like, okay,
Yeah.
so now I pushed. So first of all, I need to create a Docker image of my code. So this can be done only when the code is stable enough. Because if I'm, in heavy development, I will use other solutions, which maybe you will show in another live, which is the interactive approach. But
Yeah.
now we are
Correct.
working in a batch mode, right? So we're working with Slurm. So Slurm is meant for batch processing. So we assume that the code is already good. So we package it into a container. We push it to the container registry, which is what I just did here. Okay, so the tag is this one. So now I want to run this container. So
Yeah.
I go to my pod definition in the Slurm annotations in the pre-exec, which means before running the job, do this. So singularity pool inside this name. I mean, create this singularity image. Let's call it
So
two.
yeah, this will download the container image from the container registry and put
Yeah,
this locally, right?
yeah,
So it will
exactly.
take some time. So I'd avoid to do this right now,
Sure,
right?
sure. No, no, no,
Okay.
no. I was planning to avoid, but I just wanted to show what the user should do,
Yeah. Yeah.
and then the user now should leave this uncommented, but I will comment it. And the other thing, and this is the tricky way, let's say the error-prone part that maybe could improve, is that now I have this image downloaded, but I need to copy this path here. So, like I need to
Yeah.
say,
Good point. Good point. This is
here
definitely something that will happen automatically in the
I need
future.
to, yeah.
Yeah.
But now let's not change it because otherwise it will break everything. So,
Yeah.
so now we have our pod. Everything is packaged, is well configured. I mean, we could even use some config maps, of course. In the future, there will be also secrets.
Good.
uh,
Yeah. And yeah, just to be clear, what you're looking at when you are doing a kubectl get node. So let us know what is your Kubernetes cluster looks like.
if you want this, oh no,
Get node. Okay, so if you yes, exactly. So you see there are a lot of physical nodes. And then what you see at the bottom, there are 1, 2, 3, 4 different nodes that are virtual. So they are not actually existing. So they are not physical machines. They are either the first one, it is something that we are going to show in the next episode. It is a virtual kubelet made by Classics together with CWeb. It's particular Kubernetes based virtual kubelet, so Kubernetes to Kubernetes. And then the other ones are, you might see Leonardo, that is the Italian HPC. You see a Virgo, that is a use case, but it's also working on Vega. And then there is the Vega new virtual kubelet. So the one we are going to use, as mentioned in the node selector, is the Vega new virtual kubelet. So we are going to submit to that node, and then the magic will happen thanks to the virtual kubelet.
Yeah. So exactly, here is a bit hidden, but yeah, we're selecting this Vega new VK. So yeah, by the way, maybe I just show that these nodes that we're seeing, they are inside this cloud. Okay, so we're seeing,
exactly.
We're sort of inspecting what's inside the cloud, which by the way is not the same on which the MLFlow server is deployed, but this is the magic of cloud. So let's
just a second. There is another question asking about multi-user management. So this is a very good point. The current model that we are evaluating at Vega and also at Leonardo is a delegation of responsibility. So meaning that we can authorize multiple people to use interlink through a token or an OEDC valid token. So we can track whoever is interacting with interlink. But at this level, the entity that will interact with interlink, that will submit a job with a single account, with a single service account, will be the user services. What I mean? I mean that there will be something between the interlink and the Kubernetes cluster saying, okay, interlink, Vega in this case, trusts everything that comes from this Kubernetes cluster. So the handshake is between the administrator of the Kubernetes cluster and the HPC center. How users submit through this Kubernetes cluster is up, and how in this track is up to the responsibility to the Kubernetes cluster administrator. And this is one model. There is one other model that we are taking into account and will come soon, is using Slurm REST APIs. So this will allow us to pass the identity of the user directly to the REST call. So every single container is tracked on different Slurm account. So this is the full separation of responsibility. But yeah, there are pros and cons of different approaches. If what you serve is a service with its own accountability, like, I don't know, Kubeflow or something like that, you can expose this at Kubernetes level, decide who can access this service, and then talk with a service account with the remote counterpart. So these are the two main. One, delegate the responsibility between the two players, the HPC and the cluster, Kubernetes cluster, and the other one is more point-to-point authentication. But of course, the point-to-point authentication foreseeing that the user has already a full-fledged account in the Slurm queue. That might not be the case if you're a big group. You might want one group admin to be responsible for whatever is running inside. So yeah, pros and cons we are evaluating. This is really, now I think it starts to be a question that we are starting discussing with all the stakeholders. So yeah, I don't know if this actually answered your question, but yeah, we are in the making of understanding how to do this kind of thing. All right, so yeah, please go ahead.
Without further ado, so now I know people are interested to see. Okay, very nice, but let's see this running. So first of all, let's see the pods. Okay, I already have this. So let's clear this. Let's remove it and then we do. Okay, so now we have created a training job. So let's.
Oops, sorry.
No, please go.
Let me.
Yeah.
I thought. Yeah. Okay, just let me show you that probably, yeah, we have something running on the remote side. So we have actually a Slurm job that arrived and is running. So yeah, I'm
Can you,
passing.
can you see how many nodes is it using? Sorry, how many like GPUs? Can you see the GPU usage of that?
If I only remember how, yes, I see that it's using one node, and if someone in the chat knows how to ask this question to Slurm, it would be good. But no, at this point,
Because
yeah,
if
please
you
go ahead. So it's running. Okay, so it's still running. You see anything from the MLFlow server yet?
yes, let's go. Let's jump to the MLflow server now.
Yeah.
Let's close the loop. So let's go back to the experiments. So we
So
have
something
the
arrived at the HPC and is running, and actually is sending metrics to MLFlow. Please increase
yeah,
the zoom
yeah,
in.
sure. Let's see here. Okay, then you can see that now. So yeah, here. Oh yeah, let me go back. So here we can see there is new experiment, new run actually, which is currently running. So we can already see that there are some metrics being populated. So there are 2 steps made, but let's wait a bit more. They will get populated in real time. So this is also the nice thing of using MLflow. So MLflow gets, allows you to visualize the results of training during online, in real time. So we can already see, in the overview, some information about the job. We can see the parameters, so like the hyperparameters, and this can be used to compare models, like the optimizer name, for instance, the learning rate. Yeah, some other, let's say, number of epochs, but some other, like what is the model, lightning model that we're using, and
Cool. So looks like we did it. Demo Gadwell were
is it finished?
nice with us, right? So no, it's running.
Yeah,
It's not crashing. So I suppose it's going well.
yeah. So then if we refresh, yeah, exactly. So now, as you can see, we have more steps. Like again, like now, let's not
Okay,
look at
now
the,
it's
let's say,
for as long as I can tell, I see no jobs running.
okay, let's see, let's go also on my, yeah, it's completed. So good. So the distributed ML worked, and yeah, so just one detail for the, let's say, ML engineers and scientists. Of course, these values are meaningless from the ML point of view because we are just training on a very, very small data set. So just to prove that we can do that, right? So then we can scale up. Once we can do it once, we can scale up easily. We can also see some artifacts. So we have a model, with the checkpoints, everything is there, and yeah. So and that's it, right? So now when we
Yeah,
this
one
thing,
question that I have, if there are no other from the chat, uh, so the model that you stored probably in the next episodes are also reusable from a Python notebook, for instance, or something like that. So you
yes,
can access the artifacts from the S3 object storage and do inference, well, whatever, of these models.
yes, exactly.
Okay,
So I'm looking in the history where I was logging some models. Let's see. Well, let's go over here. Let's see. Yeah, I need to look for that a little bit, but it shouldn't be very hard to find. Let's go a bit deeper. Yeah. So in this case, yeah, we still have some other metrics, but it's not what so in this case we have a model. So let's go back here.
cool.
So we
Right.
have, yeah, you see that now we are also, not only we have a way to organize experiments. So experiments, you define like top level names, like in this case, this is just a default. So just toy example, MLflow quick start again, like a toy one, but then you can train different models. Okay, so different, let's say, experiments. So the experiment is a way to group similar runs, maybe same neural network, but with different hyperparameters or different data sets. Okay, and then for each one, you can have. Oh yeah, here we go. So we have a model saved. Okay, so here you can see that a model was created. I forgot about this column. Yeah, here. And then if we can either click here or just go in the models tab. And now we have a way to organize models. So we have, in this case, only two models. One is called, well, tracking quick start, again, like a toy example. And then we have the 3D gun light model. And as you can see, we have many versions. So every time we train, we can choose whether to save a new model version. And we can also add tags like, I don't know, let's say product, or let's say task classification. Yeah, okay, so tasks. But we can also,
All right, cool. So and then you can load. You have ways to load as Python function, something like that.
exactly. So yeah, I wanted to show that to you. If I go back, let me see if because there's, I mean, already in MLflow there is a snippet of code that you can. Let's see if I can find it from here. Yeah. So here MLflow already gives you a snippet of code with the correct, let's say, model ID that then you can use. And for instance, here you can predict on a Spark data frame, or, well, yeah, in this case it's for Spark, but you can also have with Pandas data frames. I don't know why it's not scrolling now. It's a bit, maybe MLflow is a bit, maybe because I'm zooming. Yeah. Okay. Yeah. Like this. Yeah. So I hope you can see that. These are some only some examples, but in general, the idea is that a model that we can see here on the left. So let me zoom in a little bit more.
Sorry, I muted you
When?
by accident. So I wanted to ID, but well, okay. Sorry, my
So
bad. Bad.
when was it cutting? Was it just now?
Yeah, a few
Oh,
seconds.
okay. So what I was trying to say is just that. So MLflow not only stores the model parameters, but when you save an MLflow model, it stores all the configuration that was used, plus the requirements, like all the libraries, okay, that were inside the environment. Well, maybe not all of them in this case. I see one. Okay, anyways, and then you can use these libraries to build a container just to wrap the model if you want, or anyways to replicate the environment in which the model was trained. And you can use it very in a very easy way. Like here, you also have the Conda environment with all the dependencies that were used during training. These are the model PTH, are the model weights, so the trained weights. Some stuff, some like sort of provenance information, I would call it. Okay, model summary. So like, but anyways, the bottom line of this is that from MLflow is extremely easy to take a model that is here, that you can find here in the models registry, and use it in Python to make predictions. And you can refer models using the tags, for instance. So I want the model which tag task is equal to classification, and then I don't need to remember the version number. So this,
And this will be associated also with the experiment. So the cool thing is that you have experiments, you have metrics, and then you have also registry for your models.
yes,
Right?
exactly.
Yeah.
And this is basically just to stress once more the importance of having a centralized service. Somehow,
Yeah.
once you have this centralized service, you can log to it. So imagine that this cloud, this MLflow server is central. You
Yeah.
can log to that from different HPC or different clouds, models at the same time. But then you can also get all of these models, and pull them into different HPCs or different clouds. So this also to answer the question, why are we looking into MLflow and not TensorBoard, for instance? Well, because MLflow already provides this out of the box. With TensorBoard, as far as I know, there is no a way to manage models, at least not this way. But
Yeah, and also let me add that it's tensor flow specific, right? So while
I mean, you
MLflow
can
you
also
can track. Yeah.
you can also use it in PyTorch.
Yeah. Kind of.
Honestly,
Yeah.
I never used I have to admit here, I never used a TensorBoard with TensorFlow. I always used it with PyTorch. But
All right.
because
Okay. So
I mean,
nice to know.
yeah. Yeah, yeah.
Okay.
So because in PyTorch there is like you do like from PyTorch dot or TensorFlow dot PyTorch import. Anyways, you have this class which is called the summary writer, and then from there you log everything. I don't know
Okay.
if in TensorFlow it works the same because, as I said, I never tried it in TensorFlow because I mean TensorFlow is sort of dying out. I don't know.
All right.
We need to, yeah,
I don't know. For sure, it's a use case, but it's different one. Okay.
yeah.
And so yeah, I don't know. We are 5 minutes past the hour. Or how do you feel, Matteo? Tired? Or
It's
can we
just
go
super hot,
to?
but because of the weather here. Oh my God. I mean, I'm keeping the window open, but I don't know if it's the best idea. I mean, maybe
Yeah.
you saw me drinking all the time, but there is just water, I have to say. Yeah. No, I
So
mean, yeah, that's it.
I think we can stay a bit, a couple of seconds for a
Sure.
couple of minutes for questions and answer. I had a pinned question. Right. So this one, let me show here. So do you think it's possible to run distributed workload on HPC? So I suppose, Dagnarov, please correct me if I'm wrong, that you are saying what you're saying here is kind of doing distributed TensorFlow training on different pods that are that are all running into Slurm, Slurm, let's say, cluster. So I think we have a lot of caveat in there, and probably we need to tweak together. So if you, as I suppose, probably as I know, are looking into this and you're finding issues, and we want to look at that together, or Matteo, if you're interested, we can have a chat on this definitely and see what are the limitations. Because from what I suppose, the trickiest part is to advertise the addresses of the different services or the different jobs, right? So because for the distributed training, depending on the mode of the distributed training, you might need at least all the jobs to be able to speak with an entry point, right? With
Yeah,
something.
they need to talk to each other actually. I mean,
Yeah.
all the nodes need to talk to all the nodes. But I haven't fully understood the question. So, uh, what, I mean, the way you understood at least the question, is it like you're running distributed ML using different HPCs at the same
No,
time?
I think in the same HPC,
Mhm.
suppose that you are now in Vega and you submit 10 pod running a distributed TensorFlow training.
Mhm.
Can you do that right now? I
But
suppose you need to tweak something, right?
it
At least
depends because
the address
it-
that each
okay.
node advertise, right?
I mean, in if you're using, I mean, if those 10 jobs are independent, like you're training different models, well then,
No, I suppose that they are coherent training. So
so in
the most difficult part for me is the coherent training.
so you mean you're training the same model, you just want
Yeah,
more nodes.
yeah.
So in this case, in Slurm, you just do it with one job. You just request more nodes. I don't think you can do that across multiple Slurm jobs, and in general, you wouldn't like to do that because it's much more complicated. And anyways, like Slurm already allows you to do that. Like, um, so for instance, we ran some scaling tests to test our AI library, and we were scaling to up to 128 nodes, which is 512 GPUs. But you do that from a single Slurm job. You just request 128 nodes, and then it will be Slurm that allocates these resources, and then you need a launcher. So the launcher in this for Torch, you use this Torch run. So Torch run will be executed on each node, and for each node, it will spawn 4 workers equal to the number of GPUs, so assuming there are 4 GPUs. And then it will make sure that all of these 512 processes know about each other. So there is like
Cool.
a communication backend, which is set up, but this is done by Torch run or MPI. I don't know if you can, because I probably you're thinking it's
What
more
about
in the,
TensorFlow? I think.
TensorFlow, if I remember it is also used. Oh my god, I'm forgetting now. I think it's
Yeah.
using
I don't think
API.
we have to answer right now exactly, but my question is probably there is more hope that I expected for this. But it depends really, Dagnarov, on your use case. So yeah, let's
I
keep
think
in touch.
I can.
I'm getting sure to have Matteo in the loop so we can talk about this together.
So I just checked briefly. So in general, I think TensorFlow it can work with Slurm directly. So now I remember. So basically, inside TensorFlow there is like a Slurm cluster detector. Let's say. So there is this Python object that will recognize the Slurm job allocation. So if you allocate 100 nodes, it will be. I will make TensorFlow aware of the 100 nodes and make sure to set up the communication. Perhaps the question of the question was more about like more in a Kubernetes style. Like if I allocate all of these nodes, then how do I make them communicate? So in Kubeflow there are ways to do that. There is the PyTorch job, I think it's called, and the TensorFlow job. And so there are these are sort of pre-made pods that you can let's say adapt for your model, and then you can run distributed ML on Kubernetes without Slurm, like directly on Kubernetes. But I never used that. It would be very nice, by the way, to try. So if by any chance we get to try that, I would be really interested.
Yeah, I think that was the point actually. Now I remember. So yeah. Okay, so the answer is let's give it a try. We are all here and interested in helping up. So
Yeah,
yeah.
sure. By the way, I never tried the volcano. This is also something I would really like to try. I don't know if you got to try that. It's like
No,
for
no.
yeah, that would be also again. It's sort of like you know like HPC on cloud. So again, you need some GPUs on cloud, which I don't know what we could get them, but still.
No.
That'd be,
I know, and it's also interesting. Volcano and also Q with the K are both scheduler for jobs in Kubernetes that can
yeah.
have some nice features. So yeah. Okay. I don't see any other question coming in the chat. If you have something, you have 3 seconds to type down. 1, 2, and 3. All right. So I don't know, Matteo, if you have anything else to say, or
I
otherwise.
mean, if you want, we can go. I,
Yeah, I
I
don't think we have enough
but
stamina to go ahead.
sure. No,
It's
no,
too,
no.
too hot in here, so.
No, sure. Yeah. Maybe we can keep talking. I had a question more about Dagger, but we can continue offline.
Yeah, we have something also on that, so don't worry.
No
And
worries.
all right, so let me just thank Matteo again. It was very nice stream, and I hope we will have more on this line. So thank you very much. And
Thanks for having me.
for all the people still there and following up, if you have any comment, please go ahead and drop a comment here in the videos, or if you want on the LinkedIn page that we have. So yeah, feel free to contact us as you want. And next time, as I mentioned before, we have a series of a few video, very brief, very concise, explaining how to set up MLFlow or the single point we touched so far. So kind of recap videos, and then we resume with a bit of more warm weather, the streaming on different topics. So keep up with a nice and interesting discussion, and thank you Matteo, thank you all. See you on the next video.